for the invitation. Oh, yeah, okay. Thank you, Claudio, for the nice invitation, and it's a pleasure for me to talk again in the seminar. So I think you invited me, I don't know, maybe 5 or 6 years ago, so when I was in Brazil, so I was closer. And I hope that the next time it will be presentially, but for the moment, this is what we have, I guess, Zoom, and so I'm quite happy. And today, so I will talk about a recent work. I forgot, I should have wrote it with in collaboration with Yvan Martel from École Polytechnique, and on the finite point blowup for the critical gKdV equation. So in the first part of the talk, I will recall a little bit the results and the state of the art for this equation, and in particular for the blowup problem. And then in the second part of the talk, I will try to explain a little bit, give the ideas of the proof of our new results. And so this is new for me, so I hope it will work. I will try to use the pencil with the iPad, so to try to do some at least write some computations. Okay, so so the gKdV equation, it's a nonlinear dispersive equation which reads dtu plus dx of u5 plus dx2u is equal to 0. So the linear part is dispersive, and then there is a nonlinearity. And here we put a power 5 to the u to work with an L2 critical problem. So I will explain next what it is. So yeah, so this equation, it has two geometrical invariants by some geometrical transformation. And so here we put the two transformation into one. So there is a scaling and the translation invariant. So what does it mean? It means that if U is a solution of gKdV, then yes, it's a typo, for any lambda naught positive and any sigma naught in R, this U of lambda naught sigma naught Tx, so which is defined by plus or minus lambda naught to the 1/2 U of lambda naught minus cube T lambda naught minus 1 X minus sigma naught, is also a solution. So for any lambda naught and any, this I can correct it, any lambda naught and any sigma naught in R. Okay. And so once you got that, you can just compute the L2 norm of this guy, and you see that it is invariant by this transformation. Okay, and so that's why you say that the problem is L2 critical, because somehow the scaling transformation leaves the L2 norm invariant. And so this is fundamental for all that we will say, and that's why we really focus on this power 5 in the nonlinearity here. Okay. Okay, so then gKdV is L2 critical. Then this equation, so it's what I should say is that if you lower the power, so here, if instead of 5 you, if instead of 5 you use okay, I don't know what happened, but it's fine. If instead of 5 you use a 2 or 3, somehow the equations are physical. The higher powers are not physical anymore, but then the power 2 and 3, they are also completely integrable. Okay, so this means that there is this inverse scattering method, which is for me a little bit magical, with whom you can really solve the equation completely if the initial data are nice and behave nice enough. Okay, but then when the power is higher, it's not completely integrable. So you cannot solve the equation explicitly somehow anymore. But however, it has still an Hamiltonian structure. Okay, so you have these 3 quantities which are conserved along the time. Okay, so J, which is just the integral of U, what I call m of u, like the mass, which is the integral of u square, and E of u, like an energy or Hamiltonian, which is the integral of 1/2 of dxu square minus 1/6 of u6. Okay, so those three quantities are conserved, and of course this will be fundamental in the analysis here. Okay. Okay, so I don't know what happened with my pencil, but okay, so let's go like that. And so in view of the energy, which is well defined in H1, before we can study the dynamic of the equation, we need something on the local well-posedness theory. Okay, and so the natural space is a space H1 because there the energy is well defined. And there is this very important result in the field by Koenig, Pons, and Vega, so in '93. And they prove basically that gKdV is locally well posed in H1. Okay, and by the way, the result, it works for all the nonlinearity, not just the critical one, but all the nonlinearities. But in particular, so what does it mean? So it means that any initial data that you're taking in H1, there exists a positive time, which depends on the norm of H1, and there exists a unique solution of this equation U, which describes a continuous curve into H1, okay, and which satisfies U in T is equal to 0 is equal to U naught. Moreover, the flow map is so which to U naught associates U is smooth. Okay, so here's the only subtlety that when I say unique, actually it's unique in a function space which is a little smaller than the continuous function with value in H1. So you have to build a resolution space which with more norms somehow to get the uniqueness. Okay. Okay, I don't understand. Okay. Sorry, I'm just trying something to come back. Okay. Okay, it's fine. So I will, sorry guys. Yeah, this is this one. Okay, so there is an important corollary for us of this result that then, so you have a local solution. It's like in ODE, you can always take the maximal time of existence. And so a corollary, which is also due to Koenig, Pons, and Vega, is that if the maximal time of existence is finite, then the L2 norm of the derivative of the solution blows up, but it blows up with a speed, so with a blow-up rate, as we say, so speed of blow-up, which is larger than 1 over t star minus t to the 1/3. Okay, and so let me try to explain this because it's not difficult. Actually, it's really a consequence of the local theory. So you take a small time t naught, which is strictly smaller than t star, and then you define this function. So Vsx, which is lambda naught in minus 1/2 times u, your solution, in lambda naught to the minus cube s plus t naught, and then in lambda naught minus 1 of x. So here, what we did is that we rescale exactly the solution by some lambda naughts, and we also use the invariance by a translation in time. Okay, the lambda naught, so we will fix it. So you will see why we will take actually lambda naught is equal to the L2 norm of a dx of u in t naught. Okay, so I think it will be clear in the next in the next line or in 2 lines. And so you want to compute the H1 norm of V in time s is equal to 0. Okay, so you just put s is equal to 0 into the formulation of u. And so what you get, it is lambda naught minus 1/2 u t naught lambda naught minus 1 of x in L2. And since this scaling transformation is invariant in L2, this is the same as the norm of u in t naught, the L2 norm of u in t naught. Okay, and then by using the invariance of the L2 norm, this is the sum of the L2 norm of U in 0. So this is fine. And somehow you would like to do the same for the derivative of V at time 0. And then so you do the same computation. The only difference that since you differentiate once in X, you got a lambda naught minus 1 in front. Okay, so then you also use the scaling invariance. Okay, I don't. Yeah. That's okay. And so what you get is lambda naught minus 1 dxu in T naught, the L2 norm. And so by the choice of lambda naught that we have in blue a little bit above, okay, we choose the lambda naught such that this is equal to 1. Okay. So what is fundamental here? That actually the H1 norm of V in 0 is independent of T naught. Okay. So by the local theory, you can find that there exists a time positive that I call S, capital S. But what is important that it is independent of T naught, such that V, such that we have a solution V of this problem, which is defined at least on 0 capital S. Okay. And then if I do that, I will see that the time of existence T star of my solution V, sorry, of my solution U, so it's larger than T naught plus lambda naught minus cube times capital S. Okay, and here, yes, and so if I rearrange this, it is equivalent to say that T star minus T naught, I put everything to the 1/3, so multiply by lambda naught, which is dxu T naught in L2, is larger than S to the 1/3, which somehow is a constant. Okay, so then this is exactly what I have announced here, that the L2 norm of dxu is larger than C naught T star minus T over T star minus T to the 1/3. Okay, and so this is quite important. This means that if we have blow up, okay, so if the maximal time is finite, then the blow up rate is larger than this rate here, and this rate, it is what we call the self-similar rate. Okay, so let me explain why this name of self-similar blow up rate. Here, just to fix the idea, I assume that a T star is 0, okay, without loss of generality. And then, so I just look at a solution like that. 1 over lambda T to the 1/2, and some profile phi of X over lambda T. Okay, so phi is a profile. So what I expect that this profile will somehow focus because lambda T will be a number going to 0 when T is going to 0. Okay, so here, for example, I choose lambda T a power, so T to the mu. Okay, and then I will assume that this solution is self-similar. So what does it mean? It means that if I transform it by the scaling transformation that we saw before, it is invariant by the transformation for any lambda naught positive. Okay. So if I rewrite this condition in with this specific solution, I will deduce. So on the left, I have the rescaled function. So 1 over lambda naught, lambda of lambda naught minus cube T, everything to the 1/2 times phi of X over lambda naught, lambda of lambda naught minus cube T, which is equal to 1 over lambda T to the 1/2 phi of X over lambda T. Okay, and so I want that is all for any lambda naught positive. So my only choice is that those guys are equals. Okay, lambda of lambda naught minus cube T is equal to lambda T for any lambda naught positive. But so if I have my lambda t, which is a pure power of so t to some power mu, then it means that lambda naught times t over lambda naught to the cube power mu is equal to t over nu. And if I carry on the computation, I want that this is equal for any lambda naught positive. I will find that I want that lambda naught 1 minus 3 nu is equal to 1. Okay, and so this is true if nu is equal to 1/3. Okay, so we see that 1/3 is exactly the blow-up rate for self-similar solution. Okay, and what we saw is that if we have blow-up, we blow up at least quicker, maybe equal, we don't know, but equal or with higher rate than this self-similar blow-up rate. Okay, so this was somehow what we could say about the local theory. Now, there is another very important object for this equation, which are the solitary waves. Okay, so what are solitary waves? They are solution on this form. So Q of x minus t with Q, which is a profile, so which is going at 0 at infinity. Okay. Then if you plug that into the equation, you see that Q must satisfy a second order ODE. And actually, this is a calculus exercise, okay? Maybe not easy, but you can like really do it with calculus trick. Integrate this ODE, and you find that it is you have explicit solution. So it is a power of an hyperbolic sequence. So it has really is going to 0 at infinity with exponential decay. And moreover, in this case, in the critical case, you can compute the energy of this guy, and this is exactly 0. So this will be fundamental also. Okay, so of course, when you get one of these solutions, with what we discussed before, we have the invariance by scaling and translation. We can build a whole family of solitary waves, and somehow here you will change the speed, okay, each time you're taking a rescaling. Okay. So you have a 2-parameter family of solutions. Yeah. So now, as we will see, we would like so now to see if we can say something, now that we know something about the local well-posed nest, can we say something about the global well-posed nest? Okay, and then these solitary waves are, will play a fundamental role. So actually, everything comes from this Gagliardo-Nirenberg inequality here. So it's a bound on u to the power 6 by the L2 norm of u to the square times the, sorry, to the fourth times the L2 norm of dxu to the square. Okay, but here what is relevant and important is that you have the best constant. Okay, and this was proved actually by Weinstein in '93. And so the best constant actually depends on the solitary waves Q. And since you remember we are L2 critical, the L2 norm of the solitary wave is independent of the rescaling. Okay, so it's the same for any solitary waves. And so if you use this inequality and the conservation of the energy, so I recall, so the energy in u naught at time t is equal to 0 is equal to the energy of u, which is equal to 1/2 of, so this is just the definition of the energy of the L2 norm of u dxu to the square minus 1/6 of u to the 6. So if you use this inequality here, you will be larger than 1/2 of 1 minus, you can factorize the integral of dxu to the square, and you will have 1 minus integral of u to the square over integral of q to the square. But since the L2 norm is conserved by the flow, here you can change it by the integral of u naught to the square. Okay, and then this is easy. You can see that if you choose an initial data in H1 with L2 norm strictly smaller than the one of Q, this will be strictly positive here. So you can deduce two things. First, the energy of U naught is strictly positive, and the energy of U so is strictly positive for any time. And second, then you got a bond on the L2 norm of the gradient, okay, independent of time. And since you already knew that the L2 norm of U is conserved, this will imply a bond on the H1 norm of U. And then by reapplying the local theory, you will deduce easily global solutions. Okay. So this is quite classical. And okay, that's what I was saying. Actually, the L2 norm of a solitary wave, it's equal to the L2 norm of any solitary wave because of the L2 criticality. Okay. And of course, so you have a very natural question, which is what happens with the solution when they have L2 norm larger than the L2 norm of the solitary wave. Okay. And so this problem actually, yes, and something I wanted to point out, because of course, in this talk, I will completely focus on the generalized KdV equation. But of course, this kind of phenomena, it happens for many other nonlinear dispersive equations and even nonlinear parabolic equations. And so, unlike in many other cases, so for example, in the case of the nonlinear Schrödinger equation, you don't have any, I would say, easy ODE arguments to prove blowup of solution by an obstruction argument. So if you know a little bit what happens, for example, for the NLS, you have a quantity which is called like a momentum, and then you got an identity that you can derive this momentum, and you got if you derive it twice, you got a sign, and then by using solving the ODE, you will see that you have an obstruction for the global existence of the solution. Okay. Unfortunately, for the KdV type equation, you don't have any functional like that, at least any simple functional like that. They are, but they are rather involved actually. And so the problem is difficult. Okay. And now I would like to do a small review about what has been done. Okay, so it's somehow 2 decades of work since the beginning of the 2000s. So let me do a small review. So first, I should say that there are some numerical work. So here I cite this one of Bona, Dougalis, Karakshayan, and McKinney in '95. And so there are numerical evidences of blowup. But the problem was completely open for a long time. And actually, the first results, as far as I know, rigorous results, so is due to Frank Merle in 2001. And he proves that if the initial data is negative, yes, and here I should say, I have said it here, here we are always close to solitary waves, but with a mass a little bit above. Okay, so slightly supercritical mass, say. Then Frank Merle proves that for such initial data with negative energy, you will have blowup in finite or infinite time. Okay. Then, yes, and what I should say that the proof relies on a varial estimate, so derived a little bit earlier by Martel and Merle. But that was what I was saying. This varial estimate, actually, it's quite complicated and involved. So it has nothing to do with a varial identity. Of course, it has some connection, but it's much more complicated. So it's not just an identity that you can derive and get a sign. Okay, that's what I wanted to say here. Then you have an important result also by Martel and Merle. So we keep on working on this problem. So in a paper, so in 2002, they did 2 things. So first, they were able to rule out the self-similar blowup rate, which is okay, t minus small t to the okay, to the -1/3. Okay. Yeah, and secondly, they also prove that if you have blowup, then the blowup profile, so you know something is concentrating, then it has to be the solitary waves. Okay, so more precisely, they prove that if the solution is blowing up in finite time t star, then you have some geometrical parameter, which are the dilatation and the translation, and this guy is converging weakly to Q plus or minus Q in H1. Okay, so this means that at least at first glance, the profile is Q. Okay, the blowup profile is Q. And moreover, you have a relation between lambda t to the square and sigma prime. This has to go to 1. Okay, this product has to go to 1 at the blowup time. Okay, so this we will reuse this this later. So this will be important for us. And so in the sequel, so it's a series of work. Okay, so they have another paper where they prove some blowup in finite time. So for slightly supercritical mass, also for negative energy, but this time they had to impose a decay on the right for the solution. Okay, so first you could think, okay, this is just a technical assumption, and actually it's not needed. But as we will see in the next slide, it is not just technical. It is really important to have this decay on the right. Okay, and so you see this is in the early 2000s, and then there is a gap of 10 years with no new results somehow. And finally, so 10 years later, there is an important result, okay, by Martelmer and Pierre Raphael, so which is a classification around the solitary wave Q. And so let me explain it like that. So you have, I call it the soliton manifold. So it's a solitary wave, it's a 2-parameter family of solitary wave. Okay, so it's a solitary wave which are rescaled. Then T alpha star, it's a tube around this manifold. Okay. And finally, A is the space where I will take my initial data. So as you see, it's a Q plus a perturbation, which is small in H1. Okay, so it is very close to Q in H1. But on the other hand, we also impose a decay assumption on the left. Okay, so the difference of the initial data minus Q has to decay at least okay, as y to the, I don't know, 11 or 12 or something like that on the on the right. Okay, so really you have to impose a decay on the right. If you do that, then you have a classification. So you have somehow 3 possible scenarios. Either you will blow up in finite time, and then the blow up rate is 1 over t star minus t to the -1. Or you have somehow to behave like a solitary wave, so you will converge strongly in H1, not in all H1, but a large part of H1 to a solitary waves. Okay, or you have what they call the exit. So there exists a time which is smaller than the maximal time, such that you will leave the tube around this manifold. Okay, and then somehow you don't know what is happening. Okay, and a result to complete this one is that the soliton case, actually it's a codimension 1 manifold. Okay, so this was approved later by Martelmer, Raphael, and also Nakanishi. Okay, so at this point, I wanted to draw something, but okay, I have a kind of technical issue. So look, maybe I will try to do something. I will try to stop sharing, maybe, who knows? Stop sharing and then maybe try to share again. Okay. So this seems to work. Yeah. Okay. Okay, so yeah, I'm very sorry about this technical issue. Okay, so let me try to share again. Okay, if I do that, it should work, I hope. Okay, and now I hope I am able to write. Yes, okay. Okay. Okay, so let me try to summarize everything. Yes, okay. So you have, okay, I think this was the problem. Yes, so I will do that. Okay. Okay, so say that this guy here, this is Q. Okay. So you're in a neighborhood of Q. So you are okay. So this is the L2 norm of Q. Well, this has to be a circle. And here I'm in a neighborhood of Q. Okay. And I have a complete classification. So I have a C1 manifold, which is a soliton manifold. Okay. So this is here. Okay, so this one is a soliton manifold. Okay, very good. So then, if I am inside, so let's say here, I have blowup, and then the rate is T star minus T to the -1. Okay. Then if I am, maybe I use this color, outside, it's exit. Okay, all these parts here, it's exit. Okay, so what do I know? I know that if I am in the brown part, at some point I will leave the soliton manifold. Okay, but then what is still open, what is conjecture, that then I should have global existence and scattering, and this is still an open problem. I think as far as I know, it does not be solved yet. So yeah, for if somebody is interested, it seems that it's an interesting problem. But okay, what I should emphasize is that all this classification is if I am in the space A, which is H1, but also with decay on the right. Okay, very good. Okay, so you could think, okay, this is just a technical assumption actually, because I needed to do the estimate and you will have always a classification. But it turns out that it is not the case. So that's what turns the problem yet more interesting. And so you have several results to complete those one. So one by Martel-Merle and Raphael. So they prove actually that there exists a unique solution which blows up in time also 1/T, but exactly with the mass of the ground state. Okay, so maybe if I come back here, my minimal mass blow up solution, it is here, maybe S of T. but of course, it doesn't belong to A. Okay, so it doesn't enter in this classification. That's the point. Yes. Then you have another result. Is that actually, if you don't take the initial data in A, then Martelmer and Raphael were also able to construct families of blowing up solutions, okay, very close to Q, so as close as we want in H1 to Q, but blowing up with different blow-up rates. So here you see, you have a blow-up rate of T star minus T to the minus nu, and nu is any number larger than 11 over 30. They also have the similar results, but blow up at infinity with a T nu for any nu positive. You see, so finally, I think the first result of Frank Merle in 2000 was actually the most general result you could have. Okay, so because you really have this finite or infinite blow-up rate. Okay, and there is a comment here that the lower bound 11 over 13 is probably not sharp. Okay, and what we conjecture with Yvan that we could this could be probably extended up to 1/2. And okay, why do we say 1/2? Because actually you remember this yes, here sigma prime T lambda 2 T goes to 1 that they prove is in one of the earlier paper. Then if you look at a blow-up rate as a power, then you will easily find that if the blow-up rate is larger than 1/2, then the blow-up point is going to infinity. And somehow it makes that it seems that the techniques they have used to find 11 over 13, it could be somehow refined up to 1/2. Okay, but not below, definitely not. Okay. Let me go a little bit. Yeah, and I also would like to mention this somehow related results. So in a joint work with Yvan 1 or 2 years ago, that we construct, so this time instead of a blowing up solution, we take the solitary wave, but we will find a way to make it flatter, you know, so we call that flattening solitary waves. And here we also got the whole range, so of possibilities when mu is between 0 and 1/3. So there are some of these construction are all related because we make interact a solitary wave with a polynomial tail. And so this polynomial tail will destroy the decay of the solution on the right. So if you adapt carefully the rate of the decay of the tail, and then you can really construct all those classes of solutions. Okay. But then, okay, so then the question was somehow what is the best blow-up rate possible? Okay, you know that you cannot go self-critical, and at least you have example which blows up at least with 11 over 13. So what is the best rate? Okay, and that's okay when we start thinking about it with Yvan some 1 or 2 years ago, and so we have a first result in this direction. It's definitely not the end, but we are able to construct. So this is the result I wanted to present today. A solution in H1 of gKdV as close as we want from the solitary wave Q, which will blow up with a rate 2 over 5. Okay, and 2 over 5 is smaller than 1/2, and so in this case, you see that the translation parameter, the translation parameter here, it's t minus t to the 1 over 5. So this is going to 0 when t is going to capital T. Okay, so then the solitary wave will concentrate, but instead of going to infinity, it will stop in a finite time. Okay. And so what I would like to do is to present this figure to somehow summarize all that is known about the blow-up rates now for the critical KdV. So, this is a work of Martelmer that I talk about here. 1/3 is ruled out. By the local theory, all that is below 1/3, it's also ruled out. Okay. One is the classification in A, and also, so when you have a lot of decay on the right, and also the minimal mass blow-up solution. And then there are all these results of exotic blow-up rates that they constructed, so Martelmer and Raphael, and it goes up to 11/13, but this is probably technical. Okay, so you could probably push that down here. Okay. But then with Yvon, so our results, then it's really in another regime. Somehow it's a regime where the blow-up point is finite. Okay, so it's converging to a finite point. And then we got this example 2/5. And so it really, like, I think that then you could really ask yourself, okay, but what is the best possible? Okay, and this is not clear for us. So actually we're trying to keep on working on that, but it's still completely unclear. So if this is just a single point example, or if there are more rates here. So for the moment, we don't know. Okay, but at least it is. And the next slide, which I think is interesting also, it is to compare a little bit what happens for the mass critical analysis. Okay, and okay, so if I come back to this one, somehow here we don't know, here we don't know, and here we also don't know. Okay, so we have still a lot of questions. For the mass critical analysis, then you know also that the self-similar rate in this case is 1/2, it is ruled out, and then you have the log-log blow-up. Okay, so this was proved like in a series of important work of Mer and Raphael, also in the first part of the 2000s. But then there is a work of Pierre Raphael where between the log-log, so it's 1/2 with the log-log correction, and the rate 1/t, it's roll out near one bubble. Okay, so near Q. Then in mu is equal to 1, you have the conformal blow-up. So this is just that for critical analysis, you got one more invariance, which is a pseudo-conformal transformation. And if you take a solitary wave and you apply this transformation, then you will find easily this rate of blow-up. And finally, you have also another kind of example of solution constructed by Bergen and Wang, which blows up in 1/t. And for blow-up rate higher, this is also open. Okay. So I think what is interesting with all of that you can see that there is really a difference. Okay, you could think, okay, NLS and gKdV, the critical ones, there are two critical nonlinear dispersive equations. So somehow the picture should be the same. But no, it is not the case. So at least what we prove here in our results, you have this point where you have blow-up. So maybe I'm not sure, but maybe you could have a continuum of blow-up rates here. Okay, this could be possible, maybe. Who knows? We don't know. But in the NLS case, this is completely ruled out. Okay. So between the log-log, which is and I should have said the log-log is also stable in H1 without topology. Okay. So somehow I think that our result opens new question about gKdV, but also about NLS. So like could you have some stuff happening here? Well, we don't know. Okay, so how am I doing with the time? It's
You're fine. I mean, you still have 10 minutes.
Okay, because
right?
okay, so no, I'm because what
Just,
I have,
Didier,
yeah.
may I interrupt you?
Yeah, please.
Okay, so it's about the picture on the gKdV case.
Yeah.
So the 2/5 is stable or unstable?
So okay, we don't know because our construction is by by compactness and by using argument backward in time. So we are not able to do it forward in time. Somehow.
Okay.
So
And
well, it's still open, to know whether it's stable or not. Honestly, I have no idea.
okay, great. And the 2/5 can be explained by numerology?
Yeah, so yeah, but okay, so that's what I wanted to do.
Okay,
But I'm afraid I'm not sure I will have the time in 5 minutes, so I'm a little bit worried actually. Because I have not prepared it in slides, so my plan was to do it, with the pen, but I think I was too ambitious somehow. But yeah, somehow there is a reason because we have, how could I say it? We have a new way of constructing, because when you want to construct this solution, you want a good ansatz, okay? And then of course you have an error because your ansatz is not an exact solution. And then you have to control the error. And this has been quite well understood by Yvan Martel, Franck Merle, Pierre Raphael. So we have technique at our disposal. But somehow, I think here our main new idea is to find a new way to construct an ansatz, somehow to be able to reach other blow-up rates. And then in this construction, specifically, the fact to have this rate, it's related to a construction, and we have some kind of super nice cancellation in the equation. Without this cancellation, we are really not sure that we can carry on our arguments. So at the moment, I would say that it is 2/5. It really comes from technical simplification, but we are trying to adapt it to more, to a continuum rate, but it's not clear if we can do it or not at the moment. So that's only what I could say. I'm not sure if it answers your question or.
Sure.
Okay, so let me just try to say something, at least. Okay, I will not have the time to do all that I wanted to do, but let me just try to say something. Somehow we want to look to an ansatz which is so u of tx. Okay, so I look to a solution. I know it will not be an exact solution, but I want as good as I can. So 1 over lambda t to the 1/2 w of t lambda t to the cube, then x minus sigma t over lambda t. Okay. Well, this is not surprising that I'm looking for such a solution because this is somehow the scaling and invariance transformation. But I just the only thing that I met the parameter depending also on the time. Okay. And so this is very natural, if I do that, to change variable. So to call this guy S, so I take a new time variable and also a new space variable. So I also call this guy Y. Okay. And then if I want that U is an equation of my equation, then I find that W must satisfy. So here I wanted to do the computation, but honestly, this is not difficult. This is just the chain rule. Okay. So you find that W has to satisfy this equation. okay, minus lambda s over lambda. So here I have a guy which is, when I differentiate with respect to lambda, 1/2 of w plus y dyw. And this, we call it just an operator that we call lambda w. Okay. And then I got also the derivative with respect to the translation of the parameters. So the parameters, they can depend on t or s equivalently. Okay, so now I'm really looking in the variable s. So I got that. Okay. So what I know, you know, recalling the identity from the old paper of Yvon and Frank, we know that this has to be small. So. And the other thing, so I also wanted to do the computation, but it's not very difficult, is that if you have a blowup rate higher than the self-similar blowup rate, then this guy is also small. So this is also small. Okay, so if you want to find an approximation at the first order, you have to somehow solve this equation here. And then a very good candidate, and as we saw, this has to be him, it's a Q at first order. So at first order, approximation, well, you just take WSY is Q of Y. Okay. And so now you want to do a second order approximation. And then, so it will be, of course, you have to start with Q, and then you have to correct it by a guy, okay, that let's call it VSY, okay? So plug this V into the equation. So I also wanted to do this computation, but I think maybe I will pull it also just to be sure to have the time. I will find that V has to satisfy this equation. So DSV minus dy. So here I have an operator which is minus dy squared plus 1 plus 5 q to the 4. Okay, apply to V. And this guy, we call it L just to simplify, and it is the linearized operator around Q. So Q is you have the equation. When you differentiate, it gives you this second order differential operator. Okay. So this is fine. And then, of course, I got the people coming from the second part. So lambda s over lambda q. And then I got minus sigma s over lambda minus 1 dyq. And all the other terms, they are somehow non-linear. Okay, so non-linear and small. There is some kind of a smallness here. Okay, small. Of course, here I'm doing a lot of approximation. Okay, but okay, and so normally, like in the original work of Yvon, Frank, and Pierre, so what they did, they look somehow at the approximation in separate variable. Okay, and so here the new idea is to mix all the variables. So the ansatz we will look is the following. Ansatz. This is VSY is equal to minus 2 lambda 1/2 of S theta of lambda SY plus sigma S times A1 of Y. Okay. I will tell you who are those guys. So, okay. I will tell you who are those guys. So first, A1. Okay. So A1 is a odd guy. Okay, I'm very bad. So it has fixed limits at minus and at plus infinity. And is odd. Sorry, okay. But this is somebody like that. This is not oscillating, okay? This is just me oscillating, but this should be something like that. So this is A1, and moreover, it satisfies dyl A1 is equal to lambda Q. Okay, so somehow I will be able to solve this equation with A1, but here the novelty is that A1 is an odd function, and this is very important. Okay, and okay, so here what I will say, you need to be used to like to have read a little bit the paper of Martel Raphael, but I know, at least Claudio, that you know this well, that the functions they used before was a little bit connected to A1, but it was going to 0. It was like that. So here you got 2m0, and it was going to 0 at infinity. So this was P. And somehow P and E1 are related by a resonance. So this is, I think this is an important idea, that somehow A1, okay, A1 is equal to P plus, I don't know, some numbers that I forgot, times a resonance. So R is a very nice BF function, decaying on both sides, but here you have 1 plus R. And so you have that dyl of 1 plus R is 0. So this R is a resonance. Okay. And I think that this is a that we're using this resonance somehow, and we're able to construct an antecedent of lambda Q, which is odd. And this will be fundamental, because when this comes in the energy, you will have a very important cancellation because of the because A1 is odd, and then this will allow more blow-up rate. So formally, by using this this guy, we can see, at least formally, when we look at the energy, that we could have any kind of blow-up rate. But no, of course, we want a solution in the energy space. So we cannot work with A1 like that. We have to cut it. Okay, we have to cut it, and to cut it, we use this theta. Okay, so we use this theta. So somehow we have to cut our A1. So the real profile we'll use is a cut like that with a theta, okay? And theta, what is important, that it is in the original variable. So here, if you remember, this is x. Okay. And the point that when you want to put this v in the computation, it is very important that you have, if you want here, is like if you undo the scaling transformation. So it's very important to put this 1/2 here. Okay, if you change the rate here, things will not work well. Okay, and Claudio, this is to answer your question. This 1/2, which will give us the rate 2/5. So somehow, if you want to change the rate, we have to find a way to change this guy here. To change this guy here. But we don't know how to do that yet. Okay. So it could be that it is just technical. It could be that it is something deeper. To be honest, for the moment, we don't know. Okay. And yeah, I think I already, you know, passed the time. So maybe it's a good time to stop.
Hear me? So, can you hear me?
Yeah, very well.
Perfect. If you have any question or remarks or comments, please, you can ask. So, if I understood well, you have the.
Sorry, Claudio, there was a cut.
Okay.
Okay, now I hear you. Okay.
Okay, so you have P and then you translate it by this resonance to
Yes.
form an odd function, right?
Exactly. Yeah.
Okay, so, and it is not important the fact that on both sides is just L infinity. You can cut off at both sides without problem.
Yeah. So okay. So you're right. This is the main point, because the reason why they choose P going to 0 at infinity, because somehow, of course, you know that very well. There is a sense of propagation in the KdV, and the wave are traveling to the right and the dispersion to the left. So you're always worried of what is coming to the right, and that's why you wanted to take a P, to cut the P on the right, not to cut it, but to make it goes to 0, not to have to cut it. And yes, and so this is with this cut here. In the original variable, there are some nice cancellation, and so you can still run the computation with this. But you're right. This is important here, and this is unusual. I completely agree with you. So.
And the initial data, the data that produced the blow up is in a, I mean, in a subspace of the energy space, right? You need some decay.
Okay, so this is also very important, because I have not tell all the story, because of course you have what we want is a finite energy solution. So actually we have to do a computation. Okay, so I will not do it, but I will just write the computation that you have to write the energy of you have to write the energy of your solution, and by the scaling invariance, you have you have this 1 over lambda 2, and then you would have the energy of Q, but since we are critical, this is 0, so it's not a problem. And then you have a guy which is minus Q times V, okay, which is the next one in line. And here, as we say, V, it's lambda 1/2 theta of x, A1 of y. Okay, so here, since A1 is odd and Q is even, this will be very small. Okay, if you take away the cutoff, then this will be very small, almost 0. Okay. I put it here, small. But then here we just have absorbed lambda 1/2 over lambda 2. So the rest could be big, okay? Because then if you keep on the computation, you have more term. Okay. So actually, this is not the end. We have to refine the ansatz. And this guy that I gave here, it's just the first part of the ansatz. Then you have to complete the ansatz here in order to arrive to a finite energy profile. So this is, I think, the technically, like the idea is quite simple. It is just that, but technically, what makes the paper difficult to follow is that then we have to have a lot of correction terms in order to cancel the other power of lambda. So we have cancel lambda 1/2, we have to cancel lambda 3/2, lambda 2, in order to have a finite energy solution.
Ah, okay, perfect. Perfect. More questions? No, if not, let's thank Didier again, please.
Okay.